Rimantas Zukaitis already presented in DecisionCAMP several times, and he represents insurance company in Lithuania, and but actually he is responsible for many years for rules-based approach, and as far as I know, Rimantas is an author of his own rule engine called Kraken, and it's I believe it's used in a real production environment where testing is extremely important, and this topic comes again and again during this DecisionCAMP. So let's see what the take Rimantas make, and so without any delay, move forward.
Thank you, Jacob, for introduction. So as mentioned, I was working most of my career on various projects related to the rules. We built several iterations of the rules engines, which mostly used internally in our insurance stack. And our specific approach here is that we focus on application of the rules for data validation, which brings some peculiarities about which I will talk today. Unfortunately, I will not talk about ChatGPT, and I will not even talk about DMN. I will talk about a very simple but very crucial element in rules development as testing, which is often overlooked as some lowly thing, but sometimes it brings in additional challenges when not implemented correctly. So nobody probably will object this, that testing in software development is an essential step. But sometimes we forget that proper testing is really, really hard. Fortunately, in software engineering, the testing is mature discipline. So we already have multiple different types of tests. We have approach of unit testing, integration testing, end-to-end testing, and manual testing. So for almost any ecosystem, be it Java, .NET, or whatever, we will have plenty of various libraries and frameworks which are addressing testing approaches and offer different capabilities, but they're again quite mature. And now there are popular methodologies which are considered a standard, like test-driven development, automated testing, tests running on commit gating in CI/CD pipelines, calculating coverage KPIs. So all these paradigms are matured in the focus on software engineering, so actually writing code. And we could say that developers who are working with actual code, we are like pretty well armed to do the day-to-day tasks. So now you would probably struggle to find a project or company who doesn't do unit testing, who doesn't do test automation, etc., etc. However, when we talk about business rules, this comes with certain challenges. And because what is applicable for software engineering and what is attractive for developers might not be applicable or attractive for people who are writing business rules. And the key challenges are four. So one is that there is a very high complexity. So if we are writing business rules, the space and variability of possible test cases is quite huge. So especially when we have a lot of rules which are interactive with each other, we have very high complexity, which is really, really difficult to test. Another, this holy grail of business rule approach is that we are enabling non-technical users to participate in development. So we are moving business logic from the code into the business rule definitions, and we enable non-technical users to work with these definitions and basically to participate and accelerate the development. However, this is this is a double-edged sword, because at the same time we allow more people to participate, but this lower access barrier means that we need more thorough testing, because it's much easier to make mistakes, to overlook something, and if it's not properly tested, we can potentially break system behavior in the production. The third is that once we start considering various testing approaches, the management and maintenance of the tests and the test data is quite painful. And it's related with the first point, that because we have a lot of test cases which need to be covered, if we will also follow the same approaches as we're following with software engineering, we will end up with a lot of tests, a lot of test data, and this is kind of a hurdle which we need to overcome. And the last point is when we're testing the system which employs the business rules, depending on our approach, in some cases it might be difficult to detect if there is an issue and the system is misbehaving. Sometimes it's difficult to detect and understand if the issue is in the rule implementation or it's in the application layer, which is interpreting the outcome of the rule. It could be both cases, and if we do not have tools and approaches to identify this can be quite troublesome. So I will talk about our use cases, what we're doing with Kraken validation rules engine. So we built it for our insurance platform, and the main target of this rule engine is ability to express data validation logic using business rules, because there is a lot of logic how data should be compliant with various use cases, what constraints and what conditions it should be satisfying. So we built it, and my specialty is that I was working for almost 20 years on various reincarnations of rules engines doing exactly that. So these data validation rules, as we call them, they're like a middle ground between constraints and the complex business rules, which is like a domain you guys are talking mostly about, because the constraints are usually simple and we are part of the domain. The complex business rules were defined on their own model. What we're doing here, we are providing ability to define rules directly on the domain model. And the rules are defined directly on the model attributes, and we express the validation logic, basically to say what conditions should be met to consider this data valid. And then there can be multiple rules on the same attribute, there can be references between those attributes, between those rules. And in real products, there can be up to thousands of rules of varying complexity. Most of those rules will be quite simple. For example, marking that this attribute is mandatory, this attribute should be shown or hidden in a particular case, and maybe this attribute should be defaulted to a particular value. But typically, up to 10 or 20% of those rules can be really complex ones. They either have a complex logic expressions or complex variability patterns by some dimensions. Another key aspect is that we allow to do this data validation using the same rule definitions, both on the UI and on the backend. So in a modern application architecture, this is essential because we want to have a responsive application. So the same rules are being applied in both environments. And in our stack, there is an elaborate integration layer. So basically, we execute the rules, we interpret the outcome of those rules, and provide the integration layer with the rest of the system. So for the backend, typically it's a pass or fail. If there is a validation error, or we basically stop that further execution of the request. If there is not, we pass. For the UI, we have various integrations with our UI frameworks, where we basically not only validate the data fields on the UI, but we also can manage flow of the UI. So if there is any errors, the user cannot proceed to the next screen or to the next tab, etc., etc. So all this elaborate thing was done to accelerate the development process for the rest of the developers and BAs in the company. So we provide this component where basically we can declaratively define a validation logic, and it provides zero overhead for the rest of the teams to integrate it and cover various use cases. So this is our use case, and naturally, because we are dealing with validation rules, these rules eventually need to be tested to make sure that we are working correctly. So let's see how this rule looks like. It's a very quick overview, basically to cover the specifics, and those specifics will be required to understand why we took the route I am presenting now. So basically, as I mentioned, we have a rule. The rule is defined directly on the entity in the domain. Each rule is bound to a particular attribute or a field, as we call it. Then the rule can have a condition. The condition is optional. If the condition is met, evaluated to the true, then we have various payloads, as we call them, and basically we are different rule types. There are various validation rules. There are default value rules which can modify the data. For example, a typical scenario is filling in blank values with some defaults. For validation, we also produce a error message and error code. Also, there is an elaborate mechanism to resolve dependencies between the rules. So in this case, I have a rule defined on the driver, but it's referencing risk item, a risk state CD attribute. So if there is any rules defined on risk state CD, those rules will need to be calculated before this rule is executed to make sure we have correct integrity. And also, we support various inheritance patterns in the domain, so we can define rule on the interface, and it will be applied for various entities implementing that interface. So the problem here is that we provide this very flexible way to define rules, but when we need to understand how this rule will be applied in the runtime and test it properly, it brings some additional complexity. So how these rules are evaluated? So the rules typically we are bundled to named rule sets, as we call them entry points. There can be hundreds of rules in a single entry point, and we are typically mapped to a particular use case. So, for example, quote issue, a policy issue, quote rate, etc., etc. So, as I mentioned, rules are defined on the individual attributes in the domain. But when we validate, we always pass a root entity to the engine, and the engine navigates to each entity and resolves required references. So basically, a developer doesn't need to know what rules are defined. We just pass an entity and a name of entry point, and those rules are automatically defined. So this gives a certain level of comfort, both for the developers, which are using this engine from the code, and for the business analysts, which are defining those rules, because we just define rules, and we know that this rule will be executed when it's necessary. Another level of complexity in our case is that there is this concept called rule variability. Basically, we say that we can have different variations of the same rule based on what we call rule dimension. So, for example, if we say that we have a different insurance plans, gold, silver, and bronze, we can define same variations of the same rule. So the name of the rule is the same, but we define different minimum deductible values. So this adds an additional layer of complexity from testing perspective, because if I have multiple variations of the same rule, that means I need to test them all accordingly. So all these things we basically resulting with compound complexity. So for example, we say that each rule requires n test cases to cover. So when we don't have rules, okay, we have a 0 test cases. So for example, if I have one rule, and for this one rule, I need 10 data sets to cover all possible cases. So in total, I need 10 cases to cover my behavior. If I add additional rule, which is independent, I have 13 cases. If I say that this rule is variable by some variability pattern, so I have 3 versions of that rule, again, the test cases compound. If I have a dependency from one rule to another, then we have a complex explosion because each case of this rule might influence this case of this rule, etc., etc. So far we inspected only 4 rules, but we already have 66 test cases to cover all possible permutations, which is quite complex. And from practical perspective, to do full test coverage using this approach, it's not really practical. So before doing this approach in developing this rules testing framework, which I will present, we were doing what we call typical test approaches. There are 3 bullet points, but actually there are only two real, because the first approach is just do manual application testing. So we're not testing individual rule, we're testing application behavior, and the manual tester, when testing application, he or she decides that application is working correctly, so that means that the rules are working correctly as well. Typically, this is very labor intensive because the application flow involves multiple steps which are not related to the rule testing. So for example, if I have a rule which is invoked during the quote issue, that means I need to fill out all the quote before this rule will be triggered. So this means a lot of unnecessary work, especially costly for regression testing scenarios. So when we do some sweeping changes and we need to go through all the cases, this is very effort intensive. If we talk about what we need to test some of the complex rules, that means the test scenarios which manual testers are going through will need to be aligned with rule implementation. So if the rule implementation is changed, somebody needs to notify the testers that the test scenarios need to be updated, which slows down the development. And typically we focus on UI behavior. So if the rule behavior can be observed from the UI, that's okay. If not, then we're a bit in a difficult situation. It's difficult to troubleshoot, as I mentioned, as we testing application behavior. Sometimes it's difficult to understand if it's related to the rule or not, especially when application is being developed at the same time and evolves. And typically test scenarios were not aimed to particular rules. So essentially, there is no specific rules testing. We're just doing some happy path scenarios and saying if it's okay, that means underlying rules are also okay. This is probably the worst case, worst approach. So the next step, which we tried, is try to do some automation. So we define, basically we test the rules using application REST endpoints. So we prepare some test data, invoke application endpoint. This request is processed, with some application code is invoked, and from this application code, somewhere the rule engine is being invoked. And basically from all this flow, we try to reverse engineer if a certain rule was triggered or not, and if the rule behavior was what we expected or not. Typically, it's focused on backend behavior as we're testing endpoints. The pros is that it's much easier to automate than manual testing. We don't need developer involvement, so we can use one of the multiple libraries we used for REST test point and automation. We actually have our own. and we can reuse existing infrastructure. The cons are that it's hard to achieve a coverage because, again, we are testing all the rules in the rule set. We don't have isolation of particular rule. If we want to have a good coverage, then we need to prepare a huge amount of test data. So again, if I have 10 different scenarios for a particular rule, that means I will need to do 10 different requests, which need to be maintained, which brings to another issue that those tests are fragile. So that means if there are some changes in the domain model or application itself during the development cycle, the data might become inconsistent with actual application. When the tests are failing, when somebody needs to go through this data and to understand if a test is failing because the rule is not behaving as expected, or it's failing because some of the changes. So again, this is so far not an ideal solution, especially when we want to test individual complex rules. So the last approach, or third approach, is plain old unit tests implemented in Java, as our language of choice is Java. So basically what we're doing, we're just implementing a simple unit test. In this unit test, we can build whatever fixture we want. We can prepare input data for the test. We call the rule engine and supply the whatever configuration we want. And when we can have whatever assertions we want. Basically, we get all the flexibility of the unit tests. So the pros is that it allows to test rules in isolation. It promotes the good testing practices, TDD, which we are bringing from software engineering world. The tests are declarative, we could say, but they are readable only for the developers because the assertions are in the code. The cons are that, again, it requires development effort, and this is what I consider a major anti-pattern because we have a code which depends on the configuration. In this case, the code is unit tests and the configuration are rules. That means what it kind of goes against the whole intention where we move the logic from the code to the configuration. Because in this case, if we change the rules, but in some cases the code needs to be changed as well. So it kind of messes up the development cycle. It's effort intensive because we need to write a lot of code to do a fixture. And typically it's very inefficient because sometimes we need to do like up to 50 times more code than actual testing code where we are asserting how a certain rule is behaving, because we basically need to build the whole data image from a test. Of course, we can do some utilities, etc., but again, it's effort intensive. So to work around this, we decided to build what we called rules testing framework, a very straightforward name. And basically, we wanted to take the best parts from a unit test approach, but instead of defining those tests in the code, we wanted to have them declarative in the configuration. We wanted to have the same abstraction level as rule development, because with previous two approaches, when we're testing using endpoints, the abstraction level is much higher. So we are dealing with application endpoints. When we're writing unit tests, the abstraction level is much lower. We're dealing with low-level code. So ideally, we want to have the same abstraction level, so the person who is implementing the rule be working on the same level and ideally writing the rule rule test at the same time. Supporting with different levels of granularity, so we want the ability to test the rules in isolation, test the whole entry point, the whole rule set, maybe test several rules in combination to see how they interact with each other. Again, the focus is on automation and ease of use. If we are providing a tool, it should be easy to use, otherwise nobody will embrace it. A key point is to simplify data management. So as I mentioned, As typically during the product development, we have a situation where the rules are being written at the same time as the domain and related services also evolve. So we want to minimize situations when something is breaking and the data needs to be managed manually. And no code approach, so no programming skills should be necessary to write those tests. Okay, so to do this, we wanted to first analyze what we're doing in the unit test, and basically to create a model for that. So typical approach is that we have a rule artifact, so it could be a single rule, a set of rules, or a whole entry point. We have some test data. We invoke from the code a Kraken engine. We get evaluation results, and basically it returns the whole evaluation tree. It says that these rules were executed, these rules failed, these rules passed, etc., etc. And then we write assertions using JUnit library capabilities in the code and say, okay, this rule should have failed, this rule should have passed, this rule should have not triggered at all, etc., etc. So we decided to model the same logic to move the same logic into a model from the code. So basically, we create a test definition. In this test definition, we want to have a link to the rule artifact, which is already defined, and we want to define what we expect, what the outcome of the rule execution should be. When we basically invoke a test engine, and this test engine will compare the actual evaluation rules with expected results and say that test has passed or failed. So when creating a model, we observed several things that basically each test is defined on one rule artifact. So it could be a single rule, it could be a subset of rules, or it could be the whole entry point. And each test defines an input data template. So for a specific rule, for example, if we have a rule defined on driver age, we will need to prepare a data image which contains a driver, and in this driver we'll have to set the age. And then we have multiple test cases in the same test, and we have a variability of input data, and we have variability on asserted outcomes. So basically we say, if the driver age, if the rule asserts that the driver age should be at least 18 years, we say if the age is 17, the rule should fail. If the age is 18, the rule should pass, etc., etc. So seeing these patterns, we say we can reduce the amount of test data because we create a test data template and then just vary the parts which are needed for individual test cases, which, for example, was not very possible when we're doing the endpoint validation and basically endpoint testing and creating a separate data image for each test case. So, as I mentioned, the main goal is to provide ability to manage test data effectively. So, as we say, the rules are always defined on the root object, and the most data is the same for individual test cases. We needed a mechanism to create the variations of this input data. And we need basically for each variation of input data, ability to parameterize assertions for each input data variation. So we can say, okay, let's take this policy data image. On it, we will execute these rules. And based on these input values, we expect certain behavior of these rules. So for these values, the rule should fail. For these values, the rule should pass. So we created such a high-level model. So basically, we split the whole test model into three parts. So the test definition defines the actual test logic. So it specifies on which rule artifact the test is being defined. It specifies the input data descriptor, which defines the template or input data on which rule should be executed, and it specifies expected results. The test case allows to parameterize input data and parameterize our assertions, expected results, and we also created an utility model element, a test suite, which allows us to bundle multiple test definitions into related groups. So, for example, all rules related to quote issue, or all tests related to quote issue, or all testing risk item can be included into the same test suite and executed together. So we don't have to bother and execute each test individually. Yeah, so once we came up with this model, we had to decide how to implement it. And the strategy we are embracing now is to do a DSL first approach. So DSL stands for domain specific language, and we are using ANTL library for that. It allows to create parsers and compilers for custom DSLs very quickly. Basically, you have to define a grammar syntax, and it generates a parser. So our approach is that instead of using a parser directly and working with abstract syntax tree, we create a model, as I mentioned in previous slide, and from this abstract syntax tree, we create an instance of a model, and then our testing framework works with this model. So this allows, for example, if we want to introduce further improvements later on, so for example, to build a custom UI or to build a third-party integration, they can work with this model instead of a DSL file or abstract syntax tree. And from our experience, the approach with this DSL first is very efficient one, because it's much more readable than raw XML or JSON, and it's much cheaper than building a dedicated UI, especially following modern UI approaches and using complicated UI libraries like React or whatever. So it's especially useful in prototyping phase, because we can do a model first decisions, and if we want to introduce new functionality and we want to change something, we change the model. We change DSL syntax very easily, which could be difficult if we're doing a UI first approach and building an elaborate UI or elaborate user flow, and then decide to add new capabilities. So for prototyping phase, as a poor man's user interface with DSL is very good approach, and then we can add the integrations later. And also it provides read-write capability if implemented correctly, so we can not only read the files, but if we're talking about some tooling approach, we can write with DSLs as well. So let's go quickly through how main elements of our rules testing framework look like. So as I mentioned, we have 3 parts: test definition, test case, and test suite. So the main actor here is test definition, which defines the actual test logic. And it's composed from five main parts. So basically, it's a test definition identified by the name. When we have a link to the rule artifact, so it could be a rule, it could be a list of rules, or it could be an entry point. The next step is that we define an input data, and we say we define this by specifying this input block. And the mandatory field here is the entity, which models the root entity. So in this case, we say that the root entity should be loaded from a specified JSON file, so we can take some data from actual application, store it, and use it in the tests. Or if we do not want to do if we do not want to create this data JSONs, which we need to be maintained each time the domain changes, we can set a generated keyword, and in this case, it will generate an empty entity structure using the domain model metadata. So the framework inspects the domain model and will generate a scaffolding for the whole root data image. So the next step is that we want to parameterize this input data, and this is a key aspect in test definition, because here we can take some template and specify some variables or constants and write those constants on top of existing data image. So basically, it says that in this case, I can set a driver age variable to specify JSON path. In this case, it will be the first vehicle, the driver on the first vehicle, and it will set to attribute age. And in a second, I will set a constant John to the driver name. So this allows us to quickly modify the existing data image, or if we want to have a generated data image which will be empty, so we can prefill with the data we want. Because as I mentioned previously, what we observed that especially if we're testing individual rules, most of this root data image is for us is insignificant. If we're testing, for example, rule on driver age, we need only this value. The rest of them are insignificant. So if we specify a variable, then we will have a mechanism to specify values for those variables in test cases. As I mentioned, we also have ability to specify rules variability by dimensions. So those dimensions values are also used by engine to determine which rules version should be applied in the runtime. So we can either define those dimension values in JSON, or we can also specify that it should be extracted from entity. So in this case, we will provide an entity, and related dimension values will be extracted from entity directly using our domain model framework and capabilities. So next to the last part is what we specify variables. So in this case, we say that in this test definition, we will have two variables with following names and following types. And the variables allow us to parameterize the test for each test case. So basically, we specify variables in the test definition, and in each test case, we specify variable values. And the last part is what's most important is actual assertions. So we can specify parameterized asserts, and we say, for example, in this case, that we assert for the driver.age attribute, the value will be is valid, should be considered as validity of the rule. And we have a multiple different assertions. Excuse me, I will reload the slide, I think. Yeah, I think there's some synchronization issue. So we have a multiple different assert types. We can assert validity by type, validity by. We can assert validity. We can assert that a certain error message should be generated or not. We can assert that a certain default value should be set to the attribute or not, and we can assert that a certain error message should be or should not be generated. So it's in similar fashion to the JUnit test. We have ability to define various assertions here. So then we move to the test case structure. So to the test case. So the test case actually define variability of a test, one single test case. And in this case, we specify for particular test definition, and we specify test definition name. And when we create the test cases and specify that a specific variable should be set to specific values. And then we can specify asserts which are specific to the test case. So in addition, if we want to specify additional assertion for each test case, we can add them with additional test case, additional asserts for this particular test case. So we have assertions which will be applied for all test cases, but if we want more flexibility for a particular set of values, we can define additional assertions on the test case level. Yeah. And the last part, as I mentioned, there is a test suite definition. So the test suite is just a list of test definitions, which will be executed together when a particular test definition is triggered. Okay, so let's see how this translates to actual use case. So for example, let's assume we have a simple validation rule, which validates license acquired date on insured attribute. So uninsured entity, so let's assume we have an insured and it has a birth date and it has the date when license was acquired. And we want to assert two things. With this rule, we want to validate two things, that the birth date should be before the license acquired date, naturally. I cannot acquire a license before I was born. And the next is that it should pass at least 16 years before, from my birth date to the license acquired, which means I should be at least 60 years old to get a driving license. So we have such a rule. Let's define a test definition for that. So we specify a link to the rule, specifying rule name. Next, we specify an input and we say, okay, let's generate the entity. So I do not even care about actual domain structure here, because all I need is insured entity. I know that this insured entity will be under the following JSON path in my entity, but I do not want to handle all the creation and all the handling of the whole policy image, which can be quite large. So I will generate an empty entity, and I want to inject two values into insured entity. So basically birth date and license acquired. I specify related variables. Okay. And then we model the test cases. So we say, okay, for the test definition rules insured, we want to have one test case which says that it should be valid if insured acquired license when he was at least 16 years old. And I specify two dates for birth date and license acquired, which will be injected into this entity, and this generated entity with these values will be passed to the rule engine, and this rule will be executed, and those values will be used to validate the rule. And the rest test case is a negative one. So I say that if there is less than 16 years between birth date and license acquired, the field should not be valid. So this allows us, at the same time, when we're writing DSL for the rules, we can write the test definitions. So these rules can be executed in multiple different ways. As I mentioned in the beginning, our goal was to do it to do usage of this framework as simple as possible. So a default integration pattern is using through a Maven plugin, and we generate the JUnit tests during a compilation time, and those tests are executed together with the rest of the unit tests in the project. So it gives us free integration in already existing pipelines and mechanisms. So those tests will be executed on the commit gating. So that means I cannot merge the branch which has failing tests for the rules. I cannot produce a release if there are rules failures, etc., etc. Another way to execute is using Java API programmatically. So, for example, if we need some integration from other than the compilation time, we can execute those tests by specifying parameters through the Java directly from the code. We can execute those through the REST endpoint. And also what we're working on now is to execute them interactively as part of the Rules Web Studio application, which basically is a UI to create rules and eventually test the rules without going into compilation and writing and compiling actual code. The next topic to cover here is the test granularity and coverage. So once we went through those applications, it might be doubting at first, because we can say, okay, if I have thousands of rules and for each of a rule I need to create a test definition and test cases, it might be so much work. And this is kind of repetition of the same doubts which were sounded 15 or 10 years ago when we were pushing test-driven development and test coverage for the actual production code. But as with code, the same is for the rules. So we test what is necessary, and the rule unit tests provide the ability to do exhaustive coverage of test cases. And they can test various combinations of the rules. And applicability of those unit tests is based on complexity. So if I have 1,000 of rules and 900 of those rules are very simple, which just enforce that field is mandatory or not, I can either skip writing tests for them because I know that they will work, or I can combine them to a single test and create and say, okay, execute all those rules and make sure that all those attributes are mandatory. So I don't need to deal with like complex variability of test cases, etc., because most of those rules are static. And once we covered all the complex rules with unit tests, then we can go to integration testing, and that's where the benefit of those unit tests comes into the play. Because when we do integration testing, we know that all the complex cases of those complex rules are already covered with unit tests. So we need only to make sure that those rules are actually included and we will be triggered during appropriate request or command. So we are actually included into entry point. And the same goes to end-to-end and manual testing. If we know that it's already covered by individual rules are covered by unit tests, and then the inclusion of those rules is covered by integration testing, we can focus as a typical manual tester is focusing only on happy paths. And we know that if the respective entry point is triggered, so for example, if validation, if quote issue rules are triggered during the quote issue process, it's okay. It's enough from regression testing perspective, because I know that I already have coverage of those rules in unit tests and in integration tests. So it simplifies at the end of the day, it simplifies the testing approach for the testers, because they are sure that it's already covered. In a similar fashion, like a unit test simplify the testing of all application, because if I have an issue, I know that it's already covered in unit tests. If those unit tests passed, that should be, the issue should be somewhere on the higher level. So it reduces cases when basically what I started my presentation from, that in some cases it's not clear where the issue is. It's in rule implementation, or it's integration layer on an actual application. So the further work we're planning to do is methodology to calculate coverage. So what percentage of the rules are actually covered, what percentage of test cases are actually covered, and what percentage of rules are actually triggered in entry points. Because we typically with this validation rules, we have scenarios where there is a lot of rules defined, and some of those rules are assembled into various combinations, into various rule sets, which are executed in various use cases. Some of those rules might not be triggered at all. Some of them might be triggered on various cases. So what we plan to do further using these testing approaches, also calculate coverage. And not to calculate it just a blunt metric, but to provide a metric which will be actually useful. Another area is that, as I displayed, defining test cases currently is quite effort intensive because we have to specify a lot of DSL for basically with just pairs of input values and expected outcomes. So basically what we can do, we can provide a more user-friendly format to represent that, for example, an Excel table, and from this Excel table generate those test cases on the fly. Because we are using a model-driven approach, so to write a model which will interpret this Excel table should be quite trivial. And another thing is that we could then auto-generate test definition stubs from the rule definitions themselves. As we have a rule definition in DSL, we can introspect what kind of rule there is, what kind of an expression there is, and we can generate a stub. And then the developer will need only to fill out the stub with various parameters. So the lessons learned from all this exercise. As I mentioned, we went through various approaches, both in the team developing Kraken and both as the company. And what we learned that sometimes the custom solution is the way to go, especially in utility domains like testing. So even we have a lot of different tools and approaches like REST endpoint testing, various automation frameworks, etc., etc. With this custom case where we have a elaborate rules engine and elaborate model, it was much simpler to develop a custom solution because this custom solution can address the pain points for the users using actual validation engine. Because one of the main feedbacks initially when we started using is that it's really hard to use. And when we started investigating, apparently this really hard to use was not that it's difficult to learn the syntax or to write the rules, it's difficult to understand when this rule is working or not. So this basically plugged a huge hole in development process, because now not only I can write the rule, but I can also write a test and make sure if this rule will work or not. So I don't need to go through the whole cycle of deploying the application just to make sure that the rule is working. In prototyping activities, this model-first approach is much better than what we call visual thinking or visual prototyping, because what we usually tend to do when somebody comes up with some vision and says we need a certain tool, often there is typically people are thinking in terms of UIs or some user experience, and we say, well, if I would have this application and it would have a list or a table here and I could do this and that, and sometimes it brings us to various weird solutions or various non-efficient implementation. In this case, we took an actual process. We analyzed how to model it. We created a model. For model, we used to serialize this model and to configure it. We used the DSL, which shines here because it's very efficient and very quick to implement compared to the elaborate UI. And those elaborate UIs and related tooling can be implemented later in backward compatible fashion, because we have a model which is already proven and tested and usable. And to build on that, we can provide a further UI, which could provide even more simplification, like I mentioned, with this table instead of individual test cases. Yes, so that's probably all I had.
Okay, Thank you.
Probably I didn't mention ChatGPT even once.
No, it's okay. I mentioned in questions, but we have a serious question from Bob Moore. You can answer this question. Do you see it in Q&A?
Yeah,
or
let me
should I?
switch to Q&A.
Yeah, you can read it aloud. How do you separate the expected outcome of a unit test from the rule?
Yeah, so maybe
this is a general problem with rule-based systems.
We cannot
So
hear
I'm
you,
just
Bob.
wondering if you had any ideas on that.
Bob, your mic is not working properly. Okay, but it's clear what Bob is asking, right?
yes. So maybe that's an error on my part from the presentation, because I wanted both to show what kind of rules we have and what tests we have. But actually, in our case, those are separate artifacts. We are defined in separate DSL files, and actually the rule itself, it's independent from the unit test.
Yes.
No, the question was, when you're defining the unit test, you have to specify what the outcome is.
Yes.
And so effectively what you're doing in the unit test is you're almost reproducing the rule itself. And so,
right.
you know, if you have a unit test which says you must, the difference between the date of birth and the license registration must be greater than 16, then you're effectively reproducing the rule in the unit test. And so it becomes, it's great for regression testing, but for actually the initial testing process, it's a bit problematic as to what's going on. And I mean, it's not by any means unique to you. I think if you look at all of the testing that we've been talking about, if the test defines what the outcome is, what's the test is somehow embedding the logic of the rule within it. And so you have to kind of manually define what the outcome is, because you know what the rules are. So that I think there's a general problem there.
Yes. So in no way this is a replacement for higher level testing. So in this case, when we were debating about how to do this, we were debating versus, like, with white box testing versus black box testing, where I say, okay, I can define a test on the system and I don't know what's inside. So I don't know what the rule implementations are. I know what the outcome should be. And for that, we already have an elaborate testing structure with test application endpoints, etc. In our case, the problem was that when we implemented this Kraken engine and we basically started using within the company, the idea was that every developer on the company should be able to define those tests. So suddenly we have like 300 or 400 users with various technical complexity and technical knowledge and time to define those tests, those rules. So the problem for them, they're defining the rule and we say, okay, I define these expressions and I will expect that they will work. But for some reason it doesn't. Maybe I misspelled an attribute name, maybe I misspelled something, maybe I did an error. So these tests in our case are aimed at that. So they are tied to the rule implementation intentionally. So somebody who's implementing the rule can make sure that it will work as we expect it to work. The implementation itself. What I didn't mention, there was another approach, even which I did not participate in, but there was an initiative that people started inspecting the rule models, extracting individual expressions, and testing, writing the tests on those expressions. Which kind of defeats the purpose, because Yeah.
Rimantas, I'm sorry, probably I will clarify what Bob is telling. He's telling that he wants to avoid duplication of the same variables, like he said, age less than 16, inside rule and inside your assertion statement inside test. Because when you change in one place, you have to change now in two places. And last year, Bob actually proposed how to resolve this problem, that never use constant threshold 16, for example, inside rules. If you define something like variable that comes from outside, and this variable called the minimum age, for example,
Yeah.
then you can use minimum age in both in test and in rules, something like this. Bob, am I right, or you asking more?
That's part of it, but I think the real issue, I think, is that if you write a test case where you're saying these are the variables that go in and this is the outcome that we're expecting, then you are automatically, in doing that, essentially the test case embeds what the rule is doing, and so you're essentially writing a test case which is effectively saying this because this is the outcome. You've effectively duplicated the logic of the rule within the test case, and that's particularly true for very simple rules. So you then end up in the situation where if you make a mistake in both of those, the outcome is you think the outcome's wrong. If you I mean, the other thing, from practical experience writing tests, quite often I found that when people write tests, it's actually they get the wrong outcome, and it's actually the test itself that's wrong, not the rule. And so it's a problematic area, and I'm not saying what you're doing is wrong, but I'm just sort of asking, how do we kind of try and address that situation? And it's not something that's at all specific to what you're doing. It's a general problem when you're testing rules. That how do you actually separate out the requirements, the sort of requirement definition of that rule from the actual implementation when you're trying to write out the test cases to verify that those the assertions are actually being done correctly. I mean, when Carol Ann was talking about millions of test cases, I was kind of thinking to myself, how has she worked out what the outcome of those millions of test cases is supposed to be? Because in order to do that, you've got all of these rules to compute, and so it becomes a kind of circular argument that that the output is like this because the rules said it was like this, because that's the only way I can generate my output unless I manually go through my millions of rules. I mean, Carol Ann is obviously going to correct me on that, but
yes. Yes, if it's a greenfield project, then yes, you might have to understand your rules and create your things that way. But if it's a modernization project, you just have to run through the existing
yes. I
system.
mean, I think the thing is that if you're doing something like regression testing, then it becomes much more straightforward because you have something to work on. But if it's greenfield, then it's much more challenging.
Except if you have awesome underwriters that write documentation that contains examples and examples. And they would say, in order to calculate premium, you need to do this and this and that. And you have a test case. They go through all the math to get to it. You just need to make sure that your computation of the premium matches theirs.
Yeah, but somebody's manually computing this.
So
yes, but not looking at the rules, because when they write the documentation, rules don't exist.
Yeah.
So we shouldn't even be looking at the rules. We should be looking at the decision model, because the decision model is your source of information. And so both the testing and the rules should be built off that requirement. And so if you've built off those requirements, you're going to be able to quickly find out what area has fallen down in the development, because you do have separation of duties, because you normally don't have your developers doing your test cases, except for maybe like the unit test cases. So there's like a separation here that you have two different areas going at it from two different ways, that by using the decision model that should have been signed off by business and agreed to by business, that these are the requirements, that is what should be the outcomes that both the developer and the tester build to.
I would say
Okay.
requirements in general, not necessarily a decision model, but more often it will be a Word document that contains those test cases.
And that's fine. It's just I tend to like the decision model because it actually visually and just defines what needs to be done. But whatever document you're using, whether you reverse engineer it out of a system or not, it should go into some sort of requirements document to be evaluated by business and determine business has agreed to what has been captured. And that then becomes the document that both the developers and testers work off to generate whatever they need to support that decision.
Okay, it's apparently Rimantas managed to touch very important points, and they're common for all of us vendors and practitioners, and we do this a little bit differently, but he touched many very important issues when we have already a model and we want to generate tests or manually create tests, or when we already have tests and don't have rules yet, and we see then in this case we can generate the model itself, and it brings us back to ChatGPT and generative AI. Hopefully next year we will hear more about this in more practical sense, but now we need to move forward, and that's why I like to bring to DecisionCAMP authors of different products like Rimantas, because he is talking about actual implementation, and that's very valuable for all of us. I'm sure when we listen a recording of his presentation, we will understand deeper what we missed right now. Thank you very much, Rimantas.
Thank you.
Okay, and let me stop this recording.